Good afternoon, everyone. Our lecture today talking about how we can find the built-in potential exist across the PN junction in thermal equilibrium. That means it's different from the last lecture because at the last lecture we was talking about how we can calculate the built-in potential, but between two extrinsic semiconductors. And our lecture today will be the third lecture at the PN junction series. Let's come back to current density equation in thermal equilibrium. Will dependent on it to find the built-in potential. Here, like we know, the total current density equal concentration of electron dot mobility of electron derivative as to conduction energy band plus charge, electron charge, dn derivative x to concentration of electron. We will depend on these points. At first, we know a concentration of electron at the n-type equal the effective density of the electron at the conduction band exponential Fermi level minus conduction energy band divided on Boltzmann constant temperature. Now let's take the first derivative to this equation to find the result here. 1 divided on Boltzmann constant temperature effective density derivative x to a Fermi energy level minus conduction energy band exponential the same bracket. Now, like we know and like we write here, an equal effective density of electron plus dot exponential Fermi level minus conduction band divided on Boltzmann constant temperature. That means we can put n instead of these two elements. Let's keep going. And after that, will be like that. No, we know the result of dn. dn equal Boltzmann constant temperature divided on electron charge dot mobility of electron. When we put it here and cancel the similarity elements in this equation, we will find here the last equation will be to the the last equation will be to the current density equal mobility electron dot concentration of electron derivative x to Fermi level. This equation will be important to us because I use the red pencil here because we will come back to it. And after that, from the same equation, we can calculate and we can imagine what the current density of hole what will equal the concentration of holes mobility holes dot derivative x to Fermi level. Now, when, like I said before, all our properties, all our equations will be in thermal equilibrium. Here, like we know, thermal equilibrium, the current density, the total current density will equal 0. That means Gp and Gn equal 0. We will benefit from this equation. And we can use the same equation to current density of electrons to prove the derivation Fermi level, derivation x to Fermi level equals 0. That means EF Fermi level equals 0 at the across the junction, because like we know, any derivation to any element if equals 0, that means this element is constant. No way this fact. Concentration of electron here equal effective density exponential Fermi level minus conduction energy band divided on Boltzmann constant temperature and the concentration of holes equal effective density of at the valence band to holes exponential valence energy band minus Fermi energy band divided on KT. So there is a transition region. That's important. We have transition region here at the cross junction between two semiconductors, where the concentration of electrons n is small as compared to that in the bulk in n-type, and the same situation with p-type, because here the concentration of holes, P is small as compared to that in the bulk P type. Now, this important will be the most important equation, will dependent on it to find the last result to build potential barrier at the cross junction. Here, the potential of electrons equal intrinsic Fermi level minus Fermi level. And to make this equation equal Fermi level minus intrinsic Fermi level, we will dot this equation 7.4 dot minus 1 to be Fermi level minus intrinsic Fermi level equal minus potential for electrons in n-type, like here. And we will benefit from this equation. How we can benefit, I will tell you. Here, intrinsic carrier concentration equal intrinsic carrier concentration of electron equal intrinsic carrier concentration exponential Fermi level minus intrinsic Fermi level divided on Boltzmann constant temperature. In n-type, like I said before, when I say n-type, that's mean the majority is electrons and n naught equal donor concentration, and the majority will be P. Okay, that's mean donor of electrons, donor concentration equal intrinsic carrier concentration exponential minus E phi Fn divided on Boltzmann constant temperature. That's mean just I will put this result, and I will put this result. I will put this result instead of this brackets. Yes, that's right. Now let's keep going to find the electron potential result. We will take logarithm to equation 7.5, and after that divided on intrinsic carrier concentration and take length to the both sides to be the potential electron equal minus Boltzmann constant temperature divided on T ln donor concentration divided on intrinsic carrier concentration. This equation will be 7.6, and we can delete this minus by putting intrinsic carrier concentration above and NDB bottom. Okay, similarity in the p-type will depend on concentration of holes equation, and at p-type, P naught equal acceptor concentration equal intrinsic carrier concentration exponential intrinsic Fermi level minus Fermi level divided on K Boltzmann constant T. This will be 7.7. Like I said before, we will use the same equation here, but here was to n-type. We will do the same equation, but with p-type. That's mean here E phi EQ FP equal the same result, the same bracket, without any changing. Okay. Now let's come back. Let's come going to find the last result of phi PN. Here equal NA, we will divide it all this equation on intrinsic carrier concentration and put E phi F EQ phi N instead of this bracket to be like that. After that, take length to the both sides to find the potential holes and equal sure divided on electron charge to be like that potential holes equal Boltzmann constant temperature divided on electron charge length concentration of acceptors divided on intrinsic carrier concentration, and this equation will be 7.9. After that, we will come back to the general equation and the most important equation to us to can calculate the built barrier potential, the built barrier potential at the cross junction, PN junction. We have these two results: potential for electrons, potential for holes. Just we will put a plus and calculate these two equations. After that, like we're seeing here, Boltzmann constant temperature divided on electron charge, then donor concentration, acceptor concentration divided on intrinsic carrier concentration square. Like we know, and like I said before at the last lecture, KT divided on E equal VT. That's mean the voltage, thermal potential, or we can say thermal voltage. That's mean VT ln NA and D divided on NI square. This will be 7.9, 7.10. Like we know, when we calculate the potential voltage, we found the result is 0.0259 volt and 25 millivolt. That will help us too much when calculate the questions. We will provide sometimes. That will help us, okay? And N-type, and note, it is the majority electron concentration, but in where in N-type. And like when we see N-type, that's mean N and note equal donor concentration, and P and note that's the minority holes concentration at the N-type. And the same thing with P-type, when PP note is that the majority concentration holes at the P-type, and NP-type, it is the minority carrier electron concentration and the P-type. Now, we have important notes here, this one and the next one. When N note, that means the majority carrier concentrate electron at the N-type, and the majority holes concentration at the P-type belong to different semiconductor. What will happen? This is important because we have a problem here, and because that we will prevent something. This N notes, PP notes didn't equal NI square. Why? Because that's fact. When dealing with different semiconductors, that means the majority of electrons don't equal majority of holes at P-type anymore. What that mean? That means mass action law here and different semiconductor is not satisfied. We remember mass action law because it was very important to us at questions at the chapter 4. Here, that means we don't use it anymore when we're dealing in different semiconductors. What does mean? Let's put this information at our VBI equation. That's equal VT potential voltage ln NA and D divided on NI square. What that's meaning? In different semiconductor, when we see acceptor concentration at the last lectures was equal here acceptor concentration here equal N note. That's mean the majority of electrons at N-type. But at the last lectures, N acceptor concentration was equal P. P, it was the majority hole, the concentration of holes at the P-type. That means the majority at the P-type was P. But here equal N and not. Why? Because we're dealing with different semiconductor. And the same thing with donor concentration. The last lecture was equal N. That was equal concentration of electrons. But here equal the majority concentration of holes. Why? Because we're dealing with different semiconductors. That's very important to us. And here, VBI, belt barrier potential, equal potential voltage, then majority of electrons at N-type dot majority of holes at P-type divided on intrinsic carrier concentration square. If majority electrons and majority holes belong to same semiconductor, what will happen? No way, we don't have any potential built potential at all. VBI will equal 0. Let's know why. Because here, like I said before, N naught equal N naught, the majority electron concentration at N type, here equal majority hole concentration at P type. That's mean here N naught equal P naught equal intrinsic carrier concentration. That's mean N naught dot P naught equal square intrinsic carrier concentration. Let's put this information on our VBI equation. After that, we will dealing with ln 1, and we know ln 1 equals 0 because that we don't have VBI anymore when we're dealing with the same semiconductor. Let's try this note. When the majority and minority concentration belong to same semiconductor, VBI equals 0. Like I said before, now this is exactly for the case of intrinsic semiconductor. If two intrinsic semiconductors are brought together, there exists no built-in potential. Question: why no one use intrinsic junction like that? What does mean? Why no one use intrinsic similar junction? That's mean why no one use intrinsic junction but dealing with the same semiconductor? Because we answered it before, because here concentration of electron built-in potential, because the main reason to answer this question, because both barrier potential equals 0, because like I said before, when applied it at the general equation of the VBI, ln 1 equals 0, because that all the equation will be 0. That means we must make a metal junction between two different extrinsic semiconductors. What that mean? That means at first what I told to you, I told you we can't dealing with we can't dealing with PN junction has the same two semiconductors. But here, by this trick, we can dealing with PN junction made from the same semiconductor, but with one condition: we must make a metal junction between these two different extrinsic semiconductors. But here different, and the same meaning we can dealing with the same extrinsic semiconductor, because put a metal junction here. Now let's go to explain the example 7.1. This solved example at our source. Calculate the built-in potential barrier and PN junction. Consider silicon. Here we're dealing with silicon PN junction at room temperature with doping concentration of Na. That's mean acceptor concentration equal to dot exponential 17, and donor concentration equal exponential 15. That's mean here we're dealing with the P type, that's right, because Na bigger than Nd. Now let's go on. Silicon at temperature equal 300 Kelvin. Let's use the equation of built barrier potential. Vt, like I said before, equals dot 0259. Ln NaNd divided on Ni square, like we know, at the T equal room temperature. Silicon equal 1.5 dot exponential 9. The last result will be dot 713 volts. And when Na equal exponential 16 and the exponential 15, VBI will equal dot 635 volts. Now let's solve together the exercise problem to 7.1. Calculate the built-in potential at silicon, the same element, we're dealing to the same element at T room temperature. Na equal, we have two results to Na and Nd. And at B branch, repeat part A for germanium arsenide. Germanium arsenide, that's meaning we will dealing with another Ni at room temperature, and we calculated it before. That will be easier to us because we're dealing with room temperature. But if we're dealing with another temperature, less than, more than, we must calculate Ni to each element again. Now VBI equal .736 volts, and here at the second situation when Na equal to exponential 16 and equal to exponential 15. Here VBI equal 670 volts. Now we're dealing with another element. This element is germanium arsenide at room temperature. This important element here, intrinsic carrier concentration, not 1.5 exponential 9 exponential 10 anymore. Here to germanium arsenide equal 1.8 exponential 6. Now let's put all these elements inside this equation and calculate the last bolt barrier potential. Equal bolt potential barrier, yes, equal to 2632 volts. And here, when we change the Na and Nd, the last result to bolt barrier potential to germanium arsenide equal 1.138 volts. That's it. Our lecture today is done. Thank you so much. Thank you to your patience. I will see you at the next lecture. Kendinize bakın arkadaşlar. Gelecek derste görüşürüz.